applications where if you can understand this image formation, this goes a long way in understanding many things. So he's saying that during the time the camera exposure window is open, right, and it is trying to gather intensities. So if the camera was completely still, right, and of course in this case we are saying that the scene is static, right. So which then means that scene point will come and impinge right, on a particular pixel, and your intensity will be simply that. You won't see any blur. But let's say if this camera begins to move during the time of exposure, then what will happen? So because of the fact that this camera moved, so some other scene point will come and hit the same pixel, right? More than one. It need not be 2 scene points. We don't know how many. So it is all a function of how fast this guy moves and how it moves, right? Whether it does a pure in-plane translation or for example, you could just do something crazier than that. Then whatever is going on, right, in the scene. So it's like if you were sitting, right, in that window. Okay, if you were the observer, then you would see so many scenes, right? You would see, like he said, there's one focused image, but then there are so many other sort of versions of that you're seeing because of the fact that this camera is moving. And this averaging effect, right, that you're seeing, see earlier days, okay, I mean if you see for example until about 2000, okay, people will only talk about motion blur, which was very simplistic. It was only after your cell phones and all came, right, that this topic became a hot topic. Until then it was more the optical blur that, let's say, everyone was interested in. But because of the fact that cell phones have become so light, it's very hard to hold them stable. Of course, they also have some inbuilt mechanism, but yet, okay, typically if you try to take something, and especially if you have to take it very well, it will go wrong, right? Otherwise, I mean, if you're simply taking it, right, everything looks fine. But suppose if I have to say that, oh no, this has to come well, then it's gone, right? That's what happens with me whenever I have to send some paper corrections to my student. He'll say, send me something sharp. I'll say, yes, I will, and then there'll be a shake, right? Other times it'll be fine when, let's say, right, nobody wants it. Okay, so right, it's like that. So the idea is, so earlier times, right, people had a very simple model. Also, right, I'll tell you a few things, the differences between the optical blur and this. Okay, so motion blur was of this form. So if you were to look at a PSF, so they will assume that the camera moves with a uniform velocity. This was an assumption that they made, okay, simply because, right, they didn't want to solve a harder problem than that. So moves with uniform velocity. Okay, which simply means that you're kind of, right, you move like that or you move like that, whatever, or if you're rotating, you rotate with a uniform. In fact, translation is what they used, and most of the uniform velocity, this was only in plane translation. If you look at, and that too, right, one direction, unidirectional. Then of course came, let's say, some methods that would say that it will still one dimensional. See earlier, right, people assumed that maybe, right, if there is a motion it will be like this, or maybe, right, you won't move like that, right, you won't gonna, right, go around doing a lot of things, right? Why would you? Okay, so they said let's just assume it to be in plane translation. Okay, these are all in plane translations and typically unidirectional. That means it's simply a one dimensional kernel. The PSF, right, is simply one dimensional, by which I mean that for example, right, if I try to plot HFN for this, what kind of a PSF will I get? Okay, then if you were to imagine, right, it could be that I'm moving, and since I'm moving at a uniform velocity, right, I mean, it could mean that during the time of exposure, all of this is during the time of exposure, what all is going on. So what would happen is, since you're moving at a uniform velocity, okay, so it boils down to saying that, right, you have kind of, these values at, let's say, 0th pixel, which is like when you just started to move, you didn't move at all, then you moved by 1 pixel, then you moved by 2 pixel, you moved by 3 pixel. You can also have fractional sort of a pixel, but then, right, people weren't worried about all that, because if there's a 1 pixel motion, then clearly you can see blurring effects. Anything less than that, right, they would just ignore. Okay, and all of these will have a weight. So if you had a total exposure time as TE, okay, if your exposure time of that camera is TE, then each one of them, right, will have a uniform exposure which is like alpha by TE. Or in other words, right, if you have like 0, 1, 2, 3, so it will be like 4 alpha, right, is equal to TE, so that these weights sum to 1. Okay, again, I mean, similar to any other PSF, just as you have an optical PSF, right, it simply means that the weight, right, that you're associating to every motion, every translation is all uniform, it's the same. Now this weight, right, has a very, very interesting interpretation. Okay, when you look at the larger picture, right, it will actually hit you. Okay, right now it will simply look like, okay, well, they all have a, because it's moving uniformly, therefore all of them have the same sort of share of weight, therefore each one is like alpha by t, and therefore, right, 4 alpha should be equal to t, and therefore so it's like each one, right, gathers equal amounts of intensities. Now this was a very, very simple model, and then people thought that, right, this is enough, and then people went on to kind of talk about, on a plane it could also have, let's say one dimensional kernel like that, okay, which should be at an angle, at some sort of a theta angle, but still it largely remained 1D. So the only extension that came was, instead of assuming that that basically it is along just the x-axis, right, so they would say it could also be along x and y-axis. Okay, in which case you will have translations along both directions, and therefore, right, you would have some angle theta, and typically this was all assumed to be known, and people were solving simple problems. Okay, but then one equation was known, okay, which I'm going to write, okay, which we'll interpret now. The actual larger picture, right, so g of x, right, is equal to 1 by Te integral 0 to Te. So see, Te is the exposure time. Okay, so the time for which the window is open, and then f. See, right? Why I'm saying this? This is something that you can easily relate to, because you have done homographies. That I want to kind of bring that portion back again in here. Okay, something that you did for really a pinhole camera, and right now we are also looking at really a pinhole camera. We are saying that, right, everything is focused. We are not saying there is any optical blur, but now the homography notion will again bring it back in here. So it is like f of h tau of x d tau. This is the spatial grid. Or in other words, right, what this is actually effectively saying is that, see, for example, if the camera moved, right, during the time that the window was open, so it could be that it was here, then it went somewhere, then it went somewhere, then it went somewhere, and then a long time, right, it's, so every time you can think of it as, doing some kind of a homography on f, right. So here there is a time notion, tau is your time, right. So as time goes on from 0 to Te, okay, so this camera is kind of moving around, and in a continuous case, right, you would sort of think that you're accumulating all the warped versions. By warp, I mean the whatever, right, if this camera moved by some amount, there must have been some h tau with respect to that, and that h tau is being applied on the spatial grid of f to give you a warped f, right. It could be a simple translation, it could be a rotation, right. So the real equation is this. A simplification of this, right, is that, okay, where you simply assume that h tau is pure translation in plane, unidirectional, all of that. But in general, okay, this is how it will look. But then this equation by itself, right, never gave too much insight into what you can play around with. And one of the issues with this was that, it kind of tied it down to time. So it is interesting, right, when somebody writes this equation, it was around for such a long time, and everyone would just look at it and say, okay, fine, right, we have that simpler model, go and use it. But now if you take a cell phone, okay, especially, and if you have a motion, you can't say that it is going to be pure in-plane translation and all that, right. It could be a crazy kind of motion. Now what is happening is, so the blurred image that you are seeing, G, is but several warped versions of what you would have ideally liked to see as a focused image, warped versions of warped, by which I mean a homography being applied. Okay, it is another thing whether a homography is applicable for that kind of a scene or not, but let's assume that it is applicable, in which case, right, you are taking different you're applying different homographies. I mean, we are not applying, right, it's just that that's what is going on, and all of that is getting added. So you can think of f as this, and then maybe at tau equal to tau 1, right, it had another homography, so it made f to be a rotated version. Then maybe at tau 2 there was another, and then it could go back and forth, right. You see here, we don't assume that it has to be in one direction and all. A long time, whatever happens, you could go back and forth, but then a long time, whatever you are doing, all the warped kind of all the warps, just say average them, and that should say theoretically yield you your G, which makes sense. Okay, this makes sense. But then the hard part is this time notion, right? And we all understand that why should I need time when I'm kind of talking about averages? And if I have like 1, 2, 2, some 3, 4, 5, 5, and if I had to find the average, right, I might as well look at how many times each one of them occurs, right? I mean, in those numbers, and simply add them up, in a kind of a different way. Why should I? So it's like this, right? So Here is where in 2000 or I don't know, I think 2000 or 2004, okay, around that time, I think even later than that, there is a paper, right, that kind of came out that, see, equivalently wrote this down. I'll write down, okay, what they wrote it down as. So they said this all, I mean, which was obvious. I mean, right, there isn't anything great about it, but then that changed the way you would actually interpret the whole thing. So they said this is equal to integral lambda, exactly equal to, okay, there's no approximation, nothing, equal to HP of lambda f of h lambda of x and then d lambda, where P is the set of poses, set of all poses. Now, okay, what does equality means? So what will you interpret this HP of lambda as now? See, it's like saying that, see, what it is saying is, if a camera went from here, went there, and suppose it was brought back for some reason, came back and landed again in the same homography that it was originally in, then it went somewhere else, right? So it's like saying that if you look at the sequence, suppose I write it down as 1, 2, and then maybe write 3, and then you have 4, okay, suppose each is a pose. I mean, pose 1, pose 2, pose 3, pose 4, but then after some time I come back to pose 2, maybe I come back to pose 1, then I jump to pose 4, right? It depends upon what is going on there. So if you were to look at a time trajectory, sometimes, right, it may be important for you, but as far as blur is concerned, why should I worry that 1 occurred first and then 2 and then 3 and then 4, right? I would rather say that 2 occurred twice, okay, 3 occurred only once, in this total exposure time, 4 occurred twice, and so on, right? So the HP of lambda is really the fraction of the exposure time, fraction of TE that camera spent in a pose lambda, correct? I mean, and okay, and this makes equal sense, no? So you're just saying that no, for me, I say time is not at all relevant. Averages, right? It doesn't matter what sequence I have those numbers, whichever order I put them, I'll get the same average. But now what you are saying is, you would rather rewrite this equation, you will throw away this notion of time and simply write it in this form. This sort of right, enables you to think about the whole problem in a sort of a new way. For example, right, if I had asked you a point spread function, see, if you imagine that right, your camera is undergoing, see, for example, if it was a pure translation, okay, which I drew earlier, I kind of drew a kernel, right? Now, if I asked you, how would you find out if I told you where the camera was in every instant of time, okay, which means that you would have to know what was the pose of the camera, and what you would do is, if I ask you, right, in the image, can you tell me what will be the point spread function at some place? If you knew the camera motion, you can actually find it. How? Because you would simply take the so for example, right, here, okay, I mean, I can explain that to you from this. This will be easier to explain. If you go back to the time notion, it will be hard for you. See, in this notion, right, what this means is that, you see, you agree that your PSF could be either spatially varying, or it could be just a constant. If it is pure translation in plane, like I said, the first case, that would be invariant all over, because you are simply translating the whole image, therefore all pixels suffer the same amount of blur. But then if you were to think a little deeply, so how do I then extract a point spread function at a pixel? How do I evaluate it? So what do? You come to a pixel, know the location, apply the pose on that particular location, see where it goes, and then you know the weight for that pose. So this weight is something like this, right? So it's like saying that when you're trying to gather photons, if you just stay in one pose, right, for a certain time, but then if you stay longer, okay, if you happen to stay longer in a certain pose, then it means that you're acquiring more photons, right? It could also be that you're the fleeting, I mean, right, you don't spend that much time, but then you kind of say come back again and again, right? Either case, you're accumulating more photons, correct? Either you just stay in that pose and then you just gather as much as you can, then you move. Okay, so the idea is that, right, you don't have to worry about whether the camera is moving uniformly, right, what is going on at all. You just have to worry about where is it and then in which particular pose. So you can think of the 6D sort of a trajectory. Okay, I mean, if I were to think of it as some kind of a 6D figure, right, which I'm trying to draw here. So you can think of the camera pose as something, right, that it travels in that pose. that kind of a pose space. So initially it might have been here, but then in time, right, we don't even care whether it was here first or here first. We just want to know in this pose, how much time did it spend, right? Whether it spent at one go that much time, or whether it spent initially, then came back again. It doesn't matter, right? I just want to know how much it gathered by sitting there. Okay, and that is your HP of lambda. The HP of lambda is that weight that you want to assign for that pose. Are you able to? I mean, is this something that you are able to understand, right? I mean, it just requires us to stretch our imagination a little bit more. So it's like saying that. So since you are going to be gathering more photons if you spend more time in a pose, so when you finally compute the averages, you should weigh that particular guy more, right? So here, for example, right? So here, if you see, if for some homography, if your HP of lambda is high, that means you actually spent a lot of time in that pose, and we don't care how you spent it. Okay, we are not interested that you first came and then kind of say revisited. We are not worried, right? But then how to find this is another issue. Okay, just saying that this is all equivalently this. How one finds HP of lambda in order to be able to explain a blurred image is something else. But right now, I just wanted you to understand the image formation process, because even with this, so the one thing that you also notice is that, okay, the camera, right, goes through a sparse set of these poses. But there are some cases, okay, where you actually rotate it like at a very high speed. For example, submarines and all, right, when they have a camera, they have to come up. So they kind of send this camera up within milliseconds, right? It needs to swing around at a very high speed just to know what is on the surface, and then it kind of then comes back, and then somebody has to kind of make sense out of that. That blurring and all is very heavy, because the speed at which it actually rotates, right, is so high that if you look at those images, you can't make out anything. But then you have to make sense out of that. Either a human has to make sense out of that, or you have to do one of these things in order to be able to de-blur, or to be able to remove the blurring effect and show as to what that scene might have looked like. Okay, but I'm saying normally, okay, our normal camera, when you use like a cell phone and all, it only traverses a few of these poses. You don't spend, right, so you don't walk all over this place. Just go somewhere, and you're done. Okay. And what this equation is saying is, if you can find out, right, what these things are at each particular pose, how much weight should be assigned, which is a fraction of the exposure time, then you simply warp the image by that homography, weight it by that homography, and simply, right, keep adding. If it is a discrete case, then you will have a discrete set of poses. That's what you eventually do. Right? We can't do a continuous case, so you will actually do a discretization of the poses. And then you will have a table that will say for this pose, right, this much is the weight, for that pose that much is the weight, and then you simply warp, multiply by the weight, and you see add this whole thing up. This is not valid if the object moves and all. Like I said, no, see, only for this you can have a simple model. This won't work. I mean, if there's an independently moving object and all, you're not accounting for that, no. Static scene, moving camera. That's what I said. Okay, statics. Okay, anyway, let me write that down. So I think maybe that's a very valid doubt. So only valid. Okay, so this equation is valid for static scene. So all this motion, right, supposed to be okay. The only other case, right, where it is valid is if the whole scene is occupied by one object and that object moves in this way, then it is okay. You can imagine, right? Suppose the whole scene is occupied by just one object, and that guy is kind of, say, and you could have your camera still, and that object could be moving. Then also it would apply. But normally we don't assume that one full object will cover the whole image. But suppose I asked you, right, at this point, what is a PSF? Assume that it is all spatially varying. Right? How would you find it? You don't even need the image. You just need the location of that coordinate, and you basically apply. I mean, just as you could have said, did your homography, what did you do? You applied the homography on, let's say, each of those locations, right? Except that instead of one homography, you got a bunch of them now, right? So you would apply, let's say, whatever, one h lambda, and you see where this point goes, and there. So for example, you can get some kernel, okay, on a kind of a 2D space, right? You can get something which can have any shape for that matter, okay. And unlike optical blur, you cannot a priori tell anything about this. In optical, we said it's nice, isotropic and all that, right? Typically because there is a nice aperture, symmetric, and therefore the blur and all has some symmetry. Nothing of that, right? Will this guy obey? Because you could have moved it this way, you could have moved it in another way. Nobody knows a priori, right, how these kernels might look like. But if somebody tells you that these are the camera poses that it went through, then you can actually, you can without even looking at the image, I can tell exactly what should be the kernel here, what should be the kernel, because all that I have to do is apply every post to this point, see where it goes, and then wherever it goes, so in that kernel, for that point I have a kernel, and at that particular location, right, I'll actually put, so because this is like 0, 0 for me in the kernel, and therefore if it goes here under some homography, right, then you see whatever is that value HP of lambda, okay, that will actually sit here, and then you apply the next homography, okay, you know, maybe it takes it somewhere else, then whatever is that, right, you whatever is the weight HP of lambda corresponding to that, and since HP of lambda sums up to 1, all these weights will also sum up to 1. I mean, never will you exceed the sum, you know, beyond 1. This will obey automatically.